What even happened in chapter 9?
Hello and welcome back to Calculus 2. This is section 10.2 on polar coordinates, and then we are going to transition into 10.3 calculus in polar coordinates. First section 10.2 is only on algebra and some basics of polar coordinates and what they are and what they represent, what they're used for, and so on. So we have to start this lecture reviewing or realizing what the rectangular coordinates do first. So rectangular coordinates on the xy coordinate system would take a point somewhere. To get to that point, you will go along x-axis, so you will count 1, 2, 3, 4, 5. And then you would go up 2 units to arrive at the location 5, 2. Now that location 5, 2 is given as x, y. And you can do this in 3D space as well by adding z to locate objects in 3D. So all I did is I went down the x-axis to 5 and then went up 2 units in y direction together. Or I can go 2 units in y and then go 5 forward. Either way, I am creating a rectangle between the set of axes and where the point is. Therefore, we call this rectangular coordinate system, also known as Cartesian coordinate system. Polar coordinates are also done on the xy coordinate system, but the way to get to the point is different. So this is the way the polar coordinates are. Polar coordinates have a point given as r theta. R meaning the radius, and theta being an angle. So what is happening with polar coordinates? Guys, we are going to take first order of business is to draw the radius out to whatever the radius length is. And then in the second step, we are going to swing that point at the angle theta and arrive at the final destination, and that final destination is r theta. So the first order of business is for us to draw the radius. The second order of business is to swipe out the angle, and then we have reached the location which is given in polar coordinates as r theta. So it's a very simple concept. Draw the radius, swing the radius at the theta angle. So let's do a few examples. Let's say we have to draw, say, 3 and then negative pi over 6. Well, we know that positive angles are counterclockwise, so negative angles are clockwise, and we measure angles from a positive x-axis. So to draw this, I will start my graph by drawing radius 3. So that's the first thing I do. I go out 3 units in positive x direction because I had positive 3. And then I need to go negative 30 degrees, negative pi over 6. So I put the construction line at negative pi over 6, and then I swing this to the point right there, and that point is 3 negative pi over 6. The angle is clearly negative pi over 6, it's 30 degrees, and that's the point. So I can now erase everything else, right, the construction lines and all of that kind of stuff, and I would just have a point in space, because that's all you get. R comma theta is a point in space, and we can get to that point using x and y, or we can get to that point using r and theta. Let's take a look at another example. Say you have 2 and pi over 4. Sorry, negative 2 and pi over 4. Negative 2 and pi over 4. Well, in this case, you get to draw on the negative x-axis. So let's say this is -1 and -2. Why are we on a negative x-axis? Because we have negative number for radius. Radius cannot be negative. Radius is length. Radius is always positive, right? But if you have a negative number, that means it's forced to be on the negative x-axis. So there you go, negative x. And then we have to go 45 degrees counterclockwise from that position. So that will be here in the third quadrant. All I need to do is to swing this like that. And this point over here is -2 pi over 4. So we have to start at the origin, draw positive or negative radius, and then from that point we go either clockwise or counterclockwise depending on what kind of an angle we have. So now we see that we can reach any position on the xy plane, and we also see, because the nature of the polar coordinates is that you can reach the same location with different points. Different designations for the same point. So to reach the same point over here, I can get, let's say, or 2 and 5 pi over 4. This would give me the same. If I start here, and then I have to go all the way 5 pi over 4, it will be the same point. So we have multiple representations for the same point, right? And that is just because these polar coordinates work that way. How many times do you get to go around before you arrive at a point? Well, you can go as many times as you want. This probably never occurred to you, and if you do it and cop sees you will get a ticket. But when you go into a circle, like Somerville Circle or somewhere, what stops you from driving in circle 15 times before you take the exit? Ticket, that's it. Ticket stops you from doing that, right? Or the wish not to die, because you know how the circles are in the Somerville and Flemington and all of these circles, right? You just go in it and you go, oh, and then you're out and you're, yes, right? But you can drive into the circle and then just like playing a Russian roulette, you know. You just drive 15 times around and see if you get wiped out from the planet, right? Or get pulled over for a ticket. So the trick over here is that you can get to the point quickly, or you can loop around a few times before you get to the same point. So now we see that we had the world of x and a y, where we move in rectangles, and now we see that we have a polar world in which we draw the radius and then swing that radius around to reach the point that we want. Are these two worlds connected? Well, the obvious answer is yes. First, you see that I did draw all of the polar graphs on the xy coordinate plane. Also, it should be no surprise that I can get to each one of these points by going x and then going counting y. So we should be able to connect these two worlds with equations. Now you can go and you can memorize equations, or you can reason with these equations every time. There are 4 equations, so 2 are bringing it from polar to rectangular and the other 2 from rectangular to polar. So when you think about this, you just draw a basic right triangle, and the point on the top is at the same times r theta and xy, because we can use either of the 2 coordinate systems to get there. Now what do I have? I have length of x, I have length of y, I have length of r, and I have angle theta. If you simply write out 3 trig equations and the Pythagorean theorem, you have your 4 equations for conversion. So if you go and you say, what is sine theta? Well, sine theta is opposite over hypotenuse, so y over r. and you can solve that for y, you get that y is r cosine theta. If you write a cosine theta equation, that will be x over r, and you can solve that for x, you get r sine theta. And that, as you can see, creates the set of equations which converts from polar into rectangular. Because common sense is you have r and theta to plug in on the right to get one at a time, x and a y on the left. So this is clearly from polar into rectangular, because you have to have both of these given to get one of these at a time. Now, to go the other way around, I said, well, you have, yes? Oh, yeah, you're right. I went too fast. This is sine. You can see it's sine on the side. And then this is cosine. All I did is I solved the equation for y. I'm not sure why I wrote cosine. Clearly it's a sine there. I don't know why I wrote cosine. So yeah, solve equation for y, right? And that equation gives you that one, and that one equation gives you that one. So good. So y is r sine theta, and x is r cosine theta. Yes. And that's conversion from polar to rectangular. Now for tangent theta, we have y over x, and we also have Pythagorean theorem, which says x squared plus y squared equals to r squared. Now this equation will give you that the theta is equal to inverse tangent of y over x, and that r is equal to square root of x squared plus y squared. Now you might be tempted to say, you know, positive or negative square root, but radius is never negative, it's length, right? So we have a second set of equations, and that set is rectangular into polar, because you have to have both x and a y, right? And each equation will give you one of the polar back. So now that we know how to graph a point in a polar system, and we know how to convert between polar and rectangular, it is time to understand that these two systems do not compete. These two systems complement each other. So these two systems will be used, so you either use rectangular or you use polar, and you do that by the situation you have. And we'll see, let's now talk about functions in polar coordinates, and now you will understand why these two systems do not compete but complement each other. So, functions. First off, the definition of a function and everything is the same as always. Function is a rule which assigns, in this case, right, to each theta unique r and stuff like that, right? So what we are going to have now is that the function is represented as r equals f of theta. So theta is the input, the angle is the input, and the radius is the output of this particular function. So now, when you have r equals f of theta, we want to take a look at basic polar functions that are out there. So you know how for Cartesian, I'll put it over here in a corner, rectangular, you have y equals, let's say, 3, and that graphs the horizontal line to 3. And then you have x equals to, let's say, -2, which would graph a vertical line through -2. So the most basic equations of a variable equals a number in rectangular gives you horizontal and a vertical line. This is what you learn in your elementary algebra course. Now clearly for elementary functions, In polar coordinates, we want to know what r equals a number and theta equals a number gives us, right? That will give us the most basic equations that we can get. So now we start with, let's say, r equals to 3. Well, first off, r equals to 3, it's an equation. And when you look at this equation, you say, well, what's my theta? And the answer to that question is everything. So what do you get when you have radius equal to 3 for every single theta you can possibly imagine? What do you get? Circle. You get the circle. This is circle. Because circle goes around, and if the radius is 3, radius is 3 for any and every theta you pick. You pick theta equals 0? Great. That's the 3 on the x-axis. You pick theta equals pi over 2? That's the 3 on the y-axis. You can pick any theta. Now, this is an important thing for you to understand. Guys, note that y equals to 3 is a horizontal line that goes, y is 3 for any and every x you pick. You pick x equals 1, y is 3. X equals 100, y is 3. X equals negative pi, y is 3. No matter which x you pick in the Cartesian, over here, in the rectangular coordinate system, no matter which x you pick, your y is always 3, and that's the end of the story. So now you have the same thing here. Theta is not mentioned anywhere, just like x is not mentioned anywhere in there. So theta is not mentioned, which means theta takes on all the values from negative infinity to positive infinity. Well, that's also going to take all the values from 0 and 2 pi, which is enough for us to trace the circle once. So basic equations of r equals a number are all circles with that radius. So what is the r equals? So let's write that in blood over here. R equals a number is a circle. And that's one of the basic equations. Let's box that because that's important. Now we have the next one, which says theta. Okay, let's pick something. So how about theta equals to pi over 4? Now, what is this? See, now theta is fixed. R is going to take all of the values from negative infinity to positive infinity. So what would this be? Well, let's graph. Where is the pi over 4? You see, pi over 4 is right here. Right? But then this part of the line has all r equals a positive number. This part of the line will have all r equals a negative number. So what is this? This equation is a straight line through the origin at whatever angle is given. It's a linear line through origin. In our case, it's y equals x because it's pi over 4, but as soon as you switch that pi over 4 for something else, you will get whatever slopes you get. So now, what we get for theta equals a number is a linear line through the origin, 0, 0. That's what you get for theta equals a value. Can you shift this line up and down to get some y-intercept? The answer is yeah, but it's a living nightmare. Polar coordinates are not designed for that. Okay? Polar coordinates, you'll see, are dealing with different kind of stuff. So, we've seen that there are polar functions. You know how it used to be y equals f of x? Now it's r equals f of theta. And the two very basic equations that rivaled our r equals to 3 and x equals to -2 are now r equals to 3 and theta equals to pi over 4. So our good old x and y equations are now replaced with y's and r's. With r's and thetas. Good. Now, can we prove that r equals to 3 is a circle? Well, we use a conversion. Use conversion. And then transfer that into your rectangular equation. So r is equal to 3. Well, we use the conversion r equals to square root of x squared plus y squared because that's given to us in a green box. Because green box is the link between the two. So now I have, instead of r, I have a square root of x squared plus y squared is equal to 3. Square both sides and you get x squared plus y squared equals to 9. Well, that's the circle with radius 3 in Cartesian coordinates. Yay! Right? So, circle. But see, my question to you, and this is the, pretty much when you go to the eye doctor, he's asked the same thing. What is better? This or that? Right? Which one is better? Well, clearly the polar one is better in this case because, first off, it's a function equals a number. So think of the implications for derivatives, integrals, and the future of that. When you look at this thing on the bottom and you say, well, I can't integrate that, and even if I can integrate that, I have to break it into 4 little pieces, and then I can integrate one piece, and I have to use trig substitute, just shoot me now. Right? So when you are considering this, it should be a joke to do calculus here for polar, and we already know it's a living nightmare to do the calculus on the bottom part because we have at least to use the trig substitution. So this is something that is going to be extremely important for you guys moving to calculus 3, where we do polar coordinates, cylindrical coordinates, spherical coordinates to actually deal with the stuff that it's not so easy to deal with in rectangular coordinates. So we just showed that, there's a t over here, we just showed that r equals to 3 is a circle. And we did that by conversion. Now, if polar coordinates are better, why don't we just use the polar coordinates all the time? Well, I already said it. Polar coordinates are not better, they are not worse. Polar coordinates are to be used in certain situations, and rectangular coordinates are to be used in other situations. And it will be your set skills and your knowledge and your how much you know, obviously, to figure out which one is appropriate to use and where. So let's take a look at y equals 3x plus 7. That is a straight line, linear line, and it shouldn't be an issue, right, to put something like this into polar coordinates. Well, guess what? This is an issue to put in polar coordinates. Use the conversion. Let's see. Your y is equal to r sine theta equals to 3 times r cosine theta plus 7. Well, we know that we should get r as a function of theta. So what I'm going to do is I'm going to put all the terms with r on the left and factor out. So I have r sine theta minus 3r cosine theta equals to 7. Factor out r, we get sine theta minus 3 cosine theta equals to 7. And then r equals 7 divided by sine theta minus 3 cosine theta. Look at that. So now, I'm going to do the same thing at the eye doctor. What's better? This or this? What's better? Clearly the top is better, right? Previous example, what's better? This or this, right? You get the idea. So certain equations and certain graphs are going to be better in one system, and you're definitely going to stay away from the other system in that case. Bueno? So now I'm going to work on more of graphing. Last time we talked about parameters, and we talked about the ability to break dimensions into separate dimensions and then have the parameter t drive both of those dimensions through functions. Well, now we are not doing that. What we are doing now is we are completely switching the space into the one where you used to count in rectangles to one where you are counting in circles. So by that nature, polar coordinates should clearly be better for shapes that are round. We are eventually going to combine polar coordinates and the parametric equations. Not yet, but eventually. So now, what can we do? I know that the calculators are not allowed for exams and so on, but do you guys have TI 83s, 84s with you? And the answer is probably no. All right. Now, I will try to see if this is... I want to bring up the document camera and see if this is going to work well. All right, so here is the calculator. Obviously, it's upside down. So we're going to fix that. I'm going to fix this. Do I have battery on this thing? Yes, I do. I'm going to clear this stuff. What you see over here is the XY coordinate system, right? So you see XY coordinate system. Now, if you ever examined your calculator carefully, you see that your variable button has X and then T and then theta and then N. It's not just X. That's the variable button next to the alpha button, right? So that button, by the way, those of you with non-garbage phones, you can download this app for free onto your phone, right? But if you use the garbage, then you can't. Obviously, it's garbage, which is the iPhones. If you need me to sign that, I will. Just get any other phone that it's worth having. All right. So now you have this. What I'm going to do is I am going to just show a graph, and then we'll go from there. So when I push mode button, I can change this to change the calculator to radians, and then you see already that I have a POL selected. You remember how your button has X and Y, right? So the X corresponds to function. Zoom in. There we go. So X is the funds, and T is the parametric, par, and then theta is for polar, and then N is for sequences and series. Yeah. These calculators, I know. So when you select radians and you select polar, you will see that when you go into your screen that used to be in Cartesian coordinates, what you get over here, guys, is your screen is now not F1, F2, F3. It's now R1, R2, R3 because it's expecting input to be this. Now what I'm going to do is I'm going to put over here 4 theta. And my function is 4 sine 4 theta. And then I'm going to go into, so push enter on that one. Then I'm going to go into window and just change the window so this looks nicer. This is not necessary. X minimum, and I'm going to change to -6 because of the aspect ratio of the screen. X maximum is going to be, oh, hold on, this is, it has lags, so I'm missing the keystrokes. This is supposed to be -6, that's not supposed to be there. And then X maximum is supposed to be +6. All right, there we go. And I'm going to leave and then the Y scale, I'm going to change to -4 and +4. So minimum is going to be -4. There we go. Delete, delete, -4. And then the maximum over here on the bottom is going to be +4. There we go. Perfect. And now I'm going to say second quit. We can clear this. We don't need it. And say graph. Graph. And there it is.
Oh, it's so pretty.
I know. All right. So what you have over here is a flower. Flower that has 8 petals because I had 4 theta. When you have even number, it doubles the amount of petals. If you have the odd number, it is that many petals. So 5 theta will put 5 petals, and 10 theta will put 20 petals. So even numbers double the amount of petals, odd numbers keep the same amount of petals you had. So this is the graph that you get if you simply graph 4 sine 4 theta. So 4 sine 4 theta, now you can make that more interesting over here by placing, let's say, 2 cosine of, let's say, 8 theta, right? You make it nicer. Graph, which will add this inside part of the flower and then make it nicer. So you guys can play with this thing and figure out exactly what you can do with these equations. There are equations for heart-shaped objects. We call those cardoids, right? You can do circles. You can do, these are called laminates, all these types of flowers with sines and cosines. And a whole bunch of other shapes. If you're interested, you will look up all of the different types of functions that you can have. What I want to focus on, because no graphing calculators are allowed on a test, I want to focus on how you are going to graph this by hand. And we are going to graph these guys by hand the same way you graph the parametric equations. You are going to pick thetas, you are going to compute r's, and then you will have r theta to plot on a graph, and then you will connect the dots just like in a coloring book. So going back to our tablet over here, we are going to take a look at how to graph r equals 3 cosine 2 theta. 3 cosine 2 theta. One of the things definitely you don't want to do is transform this into xy, because that is instant death. I mean, we can try that afterwards and you will see. So what do we do with this? Well, table of values. We're going to pick our thetas, compute our r's, and that will give us r comma theta to plot on this xy coordinate plane. So first, obviously, value for theta I'm going to pick is 0. And then I'm going to pick all of the values that when I double, I get the basic values. So the next one is pi over 6, right, that I can calculate, so I'll pick pi over 12. Because pi over 12 times 2 is pi over 6, and I can compute that. Then the next one would be that I can compute, after pi over 6 is pi over 4. Well, that's pi over 8, pick pi over 8. Then the next one after that is pi over 3, which is pi over 6, no coughing. And then we have pi over 2 times 2, so pi over 4, and that will give me the values to integrate, to compute from 0 to pi over 2. We'll get much more than that, but that's fine so far. So cosine of 0 is 1, times 3 is 3. So we are starting at, let's go, 1, 2, we are starting our first dot at 3. The angle is 0, which means positive x-axis. That's the 0 angle. And then we draw the radius out 3, and it stays there. The next point is pi over 12. Angle is pi over 12. Plug that pi over 12, get pi over 6. Cosine of pi over 6 is root 3 over 2. So this works out to be 3 root 3 over 2. Now, 3 root 3 over 2, calculated on the roughly, right? So we have 3 square root of 3 divided by 2 will give me about 2.6. So now, the next order of business is pi over 8. So pi over 8 is, when I plug in, it becomes pi over 4. That's root 2 over 2. So 3 root 2 over 2. So second entry, 3 root 2 over 2 gives me about 2.12, so 2.1, it's fine. Pi over 6 times 2 is pi over 3. Cosine of pi over 3 is half, so I have 3 halves. Well, that's equal to 1.5. And then pi over 4. Pi over 4 plugged in a cosine gives me pi over 2. Cosine of pi over 2 is 0, so I get the big fat 0. When the radius is 0, you are always at the origin. Nice. So what do I have? Well, I have angles of pi over 6, pi over 8, pi over 12. So pi over 6, pi over 8, pi over 12. And as you can see, we'll measure these numbers and they will do this. So as you can see, they lined up to be a half of a petal of a flower. As you draw this, it will give you half of a petal, like that. What does this picture look like as you go and pick up more points and so on? It is going to look as a 4-petal flower. That's what it's going to look like when you do all of the calculations and you do all of the... So what we got is we just got 1/8 of the entire thing in with the values that we... So it's very tedious. It takes a long time, but it's possible. So graphing in polar coordinates is the same as graphing in anything else. You use the middle school method. In middle school, you learn that you are supposed, when you get an equation, you pick your x's, you compute your y's, you plot the dots, and you connect the dots, right? So you do the same thing here. You pick your thetas, you compute your r's because you have equation, and then you have r and theta, and you plot those points, and then you connect the dots. Be careful when you're connecting the dots to connect the dots in the order you got the dots. So the first dot that we have is at 3, 0. And then the second one was the dot produced by pi over 12, so I connect directly there. Because it's 0, and then pi over 12, and then pi over 8, and pi over 6. So I have to connect those dots in that particular fashion. And we have, dot by dot, we create the entire graph for this. Now, obviously, it will take a very long time for you to compute, right, all of the other ones. Yes.
Oh yeah, I remember doing this in like our pre-calc, but we didn't like find the exact points. Like we find the furthest points from the center, and then find out if they're curved down or curved. To make
there are ways. Yeah.
But we won't get the exact points.
Yeah. Whatever makes you happy. What makes you happy?
So if I did that, like going back to
just get it right.
Whatever makes you happy, just get it right. That's the rule. So graphing in polar coordinates, guys, you can compute the points, connect the points, and then, as I said, you should know the circle. You should also know the ellipse, because ellipse is very friendly, right, in polar coordinates as well. So take a look at these things. Convert r equals 3 cosine 2 theta. All right, let's see. Well, cosine of 2 theta can be represented by use of trig identities as cosine squared theta minus sine squared theta. And then we have conversion formulas where x is equal to r. Oh no, let's not use r cosine theta, but yeah. No, we have x equals r cosine theta and y equals r sine theta. And we also have that r is equal to square root of x squared plus y squared. So let's see what kind of nightmare you're going to get as you plug this in. So r is equal to square root of x squared plus y squared. That's equal to 3 times. And now your cosine is equal to x over r. So x over square root of x squared plus y squared. And then minus sine is y over square root of x squared plus y squared. So the initial conversion gives us this. Now we square both, we multiply both sides by denominator to kill it, which will actually make this nicer. And we get x squared plus y squared on the left is equal to 3 times x minus y. Now note that there is no way to make this equation y equals everything else because the flower is not a function, right? If you draw this flower, it fails vertical line test. It fails vertical line test everywhere, pretty much, right? So it's not a function. So you cannot write this as not a function. So you cannot write it in a form y equals f of x. You can't have that. And that's why you can't. You can't simplify this. So you only have it in implicit form. And the only thing you can do is walk away, right? Now, this is one of the nice ones, cosine 2. To try to do this for sine is going to be much worse. So it has this. Again, is it a competition between two systems? The answer is hell no. What they have between these two systems is you have R and you have this equation. So clearly the one on top I can integrate, I can differentiate, I can do whatever the hell I want with it. The one on the bottom, good luck, right? So that's the case. So these are the basics of polar coordinates. The second part, or the next lecture on this, is the calculus of polar coordinates, where we discuss the derivatives and integrals. Derivatives will be calculating slope of the tangent line, just your calculus 1 did all the time. And the integrals will be calculating areas of the petals and hearts and circles and all of those kind of things. So we're going to take a short break and then do calculus of this